We ended last time talking about phase space, and I'm going to say a little bit more about that. That you can get, if you have the potential energy, you can actually sketch the phase space from just the potential energy. So for 1 degree of freedom problems, you can sketch the phase space. I guess I mean the phase portrait. From the potential energy, or more generally, the effective potential energy. Remember what the effective potential energy is? If we have some equation of motion for a scalar variable x, and x double dot equals f of x, then you can always write f of x as the negative derivative with respect to x of a potential energy, where that potential energy is the negative integral of that function x, the right-hand side of the second order ODE. And if you've got that, then you can sketch the potential energy. So if we had a potential energy that looked like I don't know, something like this, or this is our variable x, and this is our effective potential energy. Well, directly below, this is like a graphical method. We know that the hilltops of potential energy are saddle points. So hilltops, so things that look locally like a hilltop, in the phase space, they look like saddle points. So they're equilibrium points, but they're saddle points. Meaning nearby, they look like a saddle. What we might call valleys or troughs will look like there's equilibrium points, but nearby things are just sort of oscillating. And then you can put those two types of things together. So for this effective potential energy that I've plotted in red, at least for the portion I've plotted, there's just one hilltop. And I can say, okay, it's like here. There's the hilltop. So locally, I know this looks like a saddle point. And we should know lots of things about 1 degree of freedom systems that are based on an effective potential energy. They conserve, if you were to draw a straight line like this would be like the effective total energy. And the distance between the total energy straight line and the effective potential energy is 1/2 x dot squared. And we say, well, where's the m? It's because we don't have an m over here. This is just mathematically a second order ODE. So that means the further away we get from this equilibrium point, the larger the magnitude of the x dot, right? This is the x dot value, and it's plus or minus. So going both ways, that's what we have. What if we had an energy that was below that hilltop? Well, then we would have something else we've talked about, these turning points. So points where the trajectory reaches 0. So for this value, this would be a turning point, this would be a turning point. And the way that phase portraits work, nearby trajectories must be going in the same direction. So if we think of this part up here is going to the left, then this has to be going to the left and reach a turning point. Turning point means 0 velocity. So you can just sort of sketch. Over here, this is going below it's going, x dot is negative, so this is going to the left. So this would be what an example trajectory would look like. If we had an energy that's above both, then it would look like, I'll write this in orange. It would have its lowest velocity when it's above or near or passing through the hilltop, and then it would go on like that. If you're wondering, how do I know what direction to plot the arrows? It's because this upper half plane, x dot is greater than 0. So x is increasing, which means going to the right. So arrows to the right. Below, x dot is less than 0. So x is decreasing with time. So arrows to the left. So this would be what we might call the graphical method to estimate the phase portrait. And you could do this for any potential energy. So what if I just sketch something like something like that, and I say, well, this is my either potential energy or effective potential energy. You could sketch below what this is. So let's call this x dot, and this x. Wherever we have a hilltop, we've got, I'll put those in red, hilltops. We've got a saddle point. We have an equilibrium point. Maybe that's the first thing to know. We have equilibrium point. Equilibrium point means x dot is equals 0. There's no motion. And since they're hilltops, we know locally that we've kind of got an X marks the spot situation. We've got these saddle points, and we even know what direction the arrows are going because of what we talked about. X dot positive means things are moving to the right, more or less. X dot negative, things are moving to the left. Okay, what about these others, these valleys? Well, those are also equilibrium points. If you start there, you stay there, but they're oscillatory, meaning if you start a little bit away from it, you'll just sort of oscillate back and forth. And what that looks like in terms of, and this is just locally, this is what it looks like in the phase space. It looks like a bunch of closed curves oscillating. We haven't added damping yet. If you add damping, then other things could happen. So that's sort of what you would sketch locally. And then to know how things are connected, you would plot straight lines and say, okay, passing through this middle hilltop point, I would have trajectories that have turning points at these two locations. And what that allows me to do is say, okay, a trajectory that's going away from the saddle point, it'll, conserving energy, it will actually, when it's above the valley, it'll have its largest velocity, and then it'll go to a velocity of 0. And then it would do a mirror image of that coming back. And we could do that on both sides. So it's almost like that, this sort of red curve that I've shown is the maximum extent of the oscillations in each of those wells. Well, what if I have an energy slightly above that? Well, I'd have something that's, it's got turning points. It'll reach a maximum velocity at these two locations, minimum velocity other than 0 at that location. And it has turning points. So this is a trajectory which is oscillating, but going through both wells. And then let's just suppose that these two are at the same energy, that means that this red trajectory and these trajectories can't intersect one another. So we would have something like this, and we don't know what's going on elsewhere because we just haven't plotted that. Then something outside look like that, and then add arrows for good measure. So that's a sketch of the phase portrait. And you'll notice there's different, we could even start looking at different types of behavior here. If something was oscillating completely in the left well, this is the set of initial conditions that are oscillating only in the left well. And then in yellow, we have things that are oscillating only in the right well. In purple, we've got things that are oscillating. These are trajectories that would have motion that's oscillating about both wells. And then outside of that, we have things that could, maybe they're not oscillating. Maybe they're going off to infinity, plus infinity, and so on. Okay. Now, if we add damping, that would change things. Or dissipation. So suppose we add linear damping. So in something of the form negative Cx dot, where C is greater than 0. So that means our second order ODE would look like this. There's a part that's conservative because it conserves energy. And then we have negative Cx dot. Well, then this, what did I have up above? Yeah, this potential energy, I'll do this potential energy. If we had this as our potential energy, then what would we get down below? We would have this situation. And this is calling this Y, but this is just X dot. This is X. So we would have, using the same colors as up above, now in yellow, we've got everything that will end up in the right hand equilibrium point. And in blue, everything that will end up at the left hand equilibrium point. And what's going on here? Well, we still have a saddle point at that hilltop in the middle. And at these valley points, we've got things that are now spiraling in. So damping, if you add damping, then you have things that go from being closed curves to everything is spiraling in. So we can easily imagine this. If we had a ball moving in this well, we release it somewhere, it's going to eventually settle down in one of these valleys. And there could be interesting things like if I released over here somewhere, if I release at this point or at this point, I'll have two different fates. Or think of releasing from rest at, I'll make it a different color. This point down here, and then nearby, if I released at this point, these two balls would settle down in the two different wells. And in fact, I have a student who did this experiment. So he came up with a curve, and he literally turned this into a track. So he made a wooden track, and here he is releasing the ball from rest on the left side. And it's not easy to predict which one it'll end up in. Oh, okay. it settled down in the left well. He did some processing where he could digitize this and then see where it ended up, and then like track the center of the ball, get the X value for that. And then since he's getting this at equal, at a certain frame rate, equal time steps, he can get X and X dot and even plot a phase portrait. So this is showing releasing from this position up here in the upper right, where did this thing settle down? And you can see it spirals. It's spiraling into the equilibrium of the left side of this little track. So the terminology for what's being shown here is that yellow is the basin of attraction for the right equilibrium point. So everything that's yellow, we say it's the basin of attraction, meaning things will end up there of the right equilibrium point. Stable, the right stable equilibrium point. And then in blue, this is the basin of attraction of the left equilibrium point. And I've only shown this out to some certain value, but right, these spirals keep going around and around and around. So if you wanted to, you could think of this as if you were to release at rest, there are, I'll plot it over here on the left side, there are certain regions where if you release it, it'll end up in the right equilibrium. And then right next to it are places where if you release it, it'll go into the left. And these will just keep alternating. So that is that's some phenomenology that's good for you to know. Okay, what's some other phenomenology? Bifurcations. Let me tell you about bifurcations. That's hard to read. Bifurcations. So this has come to mean when you have changes in behavior as you change parameters. So for example, from that homework problem where we've got the spinning T thing, it's the giant spinning blade. It's not a blade. That's a nice example. So there's this rotating shaft, and connected to it is it's a planar pendulum, but it's T-shaped. Actually, let's start it out facing down. So here, what is the main parameter? The main parameter is the speed of the motor. So the speed of motor is an important parameter. Because as we change that parameter, the behavior will change. You could think of it in terms of if you've done this problem, you'll have that theta double dot equals something. That's a function of theta and omega. So we might say we have theta double dot, right? Theta double dot is the angle that this thing makes with the vertical. It's a function of theta, and then we might put a semicolon here. So it's a function of this as a variable, something that can change in time, and it's a function of this parameter, omega. which we think of as, for any given situation, we think of it as fixed, or maybe we change it slowly. And because this is, in terms of variables, it's just a function of theta, not theta dot, we can write this as the negative potential, effective potential as a function of theta, and just sort of tack on, it's a function of the parameter omega. And this changes shape depending on if you have the speed of the motor, capital omega, greater or less than some critical value. So for omega less than a critical value, so that means slow, slow rotation of the motor, we've got a potential energy plot, or effective potential energy plot, that looks like it just has one, it looks U-shaped. There's an equilibrium point at the bottom, and that's it. What about if we crank up the motor, so now we're faster. So this is fast rotation, a fast motor. Then this potential energy changes shape. It goes from being just U-shaped to looking something like what I sketched up above, where it's like a W shape. So that we'd say that going from here to here, there was a bifurcation, because there's a qualitative change in the dynamics between these two situations. And maybe you could see what it is. For this upper situation, for slow rotation, the T shape, at least in terms of its angle theta, is just going to oscillate around the bottom position. But once you crank up this motor fast enough, well, now that bottom position becomes unstable, and you've got stable equilibria on either side. So that's a qualitative change. So, and that all falls under terminology that we say there was a bifurcation. So in this case, new equilibrium points show up. And the middle one changes stability. So that's a big deal. What does it mean for this actual system? What you're told in the problem is, okay, you start with this T shape in the bottom, facing down, and you spin up the motor, and you know that, well, as long as I'm below critical motor speed, that's a stable point. But at some point, once I'm above critical, and I think you're given a specific value of like go to square root 3/2, the critical value. Now that downward position is unstable, and any small perturbation will send it going away from the bottom position. So to use the, what we've been talking about, it'll actually shoot out and go toward these turning points. If we were to plot right below, what does the phase portrait look like? Well, this bottom point, this middle point is a saddle point, and it's going to have some turning points. So that is the extent that the T shape can shoot out to, whatever this is. We'll call that theta max. And it can shoot out either way. Maybe we'll call that negative theta max. So if we were to look at how this thing could move, if we've got omega at that certain critical value, or above the critical value, I think it's this square root 3/2, then this T shape can, even though it starts in the downward position, it could shoot out to theta max. And so you've got to figure out from what's the distance from the center line that you want to stand so that you don't get hit by this piece of machinery. I mean, imagine it's really big and you're really small. So how far do you want to be so you don't get hit? And you can even find out what this D max is analytically, because this curve, this red curve, conserves the effective energy. All of them, every trajectory conserves the effective energy, which would be 1/2 theta dot squared plus U effective. And you know what it is at the origin, where it starts out. So you can try that out. Let me give you a working definition of bifurcation. Is a qualitative change in the behavior of a system as a function of parameters. And there might be more than one. And this idea of bifurcation isn't just limited to mechanical problems or mechanical systems. This is seen in all types of things. Sometimes it's related to this terminology that is in the popular press called tipping points. So if you say like, oh, climate change has reached a tipping point, you could understand that in terms of if you were to mathematically write out what the system is, some qualitative change has occurred. There's an example I remember of the the fish population. So I know this is totally unrelated to mechanics, but the fish population of some fish, I don't know what it is, maybe it was cod, that's caught in, off the coast of New England. For many years, it was, this is how much they would catch. And so that was proportional to the fish population. And then one year, it dropped. So some kind of tipping point was reached. But you could also understand that in terms of a bifurcation, where maybe there was some kind of stable point to the population, and then that stable point changed. What's the parameter here? The parameter, I think they figured out it had something to do with the sea surface temperature. So as sea surface temperature changed, the stable population of fish that could be supported changed and collapsed, actually. And this was a big problem. I think this was like in the 90s, but you could look that up. Any questions about this bifurcation stuff or phase portraits and whatnot?
So,
no? Yeah, go ahead.
So this thing can like come back, right? Like I'm just trying to wrap my head around that thing. So like in the case of our motor, or in the if the omega once again goes below critical point, like you can get back, or in the case of the fish population, if the temperatures change back, then am I?
I don't know about the fish. The
Okay.
fish might be just gone for good. For this mechanical system, I guess if you're asking, okay, I've turned the motor up to this high value, what if I turn the motor back down?
Mm-hmm.
If you turn the motor back down, I guess it depends on where the state of your system is. So here, let's suppose it's at this point A. and then you turn the motor back down to something really low, well, then you'll be kind of back into this well, and it'll move back and forth. So it'll still be oscillating. It won't be stuck in the downward position. If you were to go at this point B, where it's reached sort of its maximum, then it'll be on a really large oscillation back and forth. If you were to stop it right at the origin, so you wait until this thing is as close as possible to the origin and then turn down the motor, well, then you'd be back in a very low or almost standstill motion. So yeah, it is reversible.
Okay, thank you.
In fact, and I wonder if this is the place to mention it, bifurcations are sometimes summarized in what are called bifurcation diagrams. And these are useful ways to kind of summarize. So let's suppose we were to say, for our mechanical system, we want to write where are the angles of equilibrium as a function of our motor speed. And I'll use blue or light blue to indicate stable point. At some point, we reach that critical value. And after that critical value, the middle point becomes unstable. The downward position becomes unstable. And we have these two branches that open up parabolically that are stable. So this is called a bifurcation diagram, and you can kind of view it as, so I'm plotting blue as stable, and this, I guess it's maroon color, it's unstable. Sometimes they'll use dashed lines to indicate instability. And so you can think of, if things are stable, then the dynamics tends to want to go towards them. If they're unstable, dynamics goes away. Oops, yeah. So bifurcation diagrams can be useful to understand what's going on. It also helps you understand what might happen if you were to reverse things. So if I'm over here, I'm using some operating point far above critical, but then I go back, well, then I'll still be back into this regime, and that regime's not gone forever. Things are more complicated for like an ecological problem, so I can't even comment on that.
Thank you.
All right. Good question. All right, now we're going to go back to Lagrangian mechanics, because there's some things that we need to discuss. And it's dealing with constraints. So sometimes you can't avoid constraints. One of those cases is if you have nonholonomic constraints, then you can't avoid them. And if you remember, when we were talking about D'Alembert's principle, I said, well, there's two cases. One of the cases is where the number of degrees of freedom equals the number of generalized coordinates, in which case you have a minimal set and you don't have to worry about constraints. The other case is if you have more generalized coordinates than degrees of freedom. So and that's the case where constraints are unavoidable. If constraints are unavoidable, or maybe you want to know the constraints because eventually we're going to figure out what the forces of constraint are in the Lagrangian method. For your last homework problem, I'm not asking you to find the constraints using the Lagrangian method. You do have to get the forces related to the normal reaction force of the wall and the floor because it goes into the Coulomb force. But you could just use the usual Newtonian way. You just have to write those in terms of theta and theta dot. I'm talking about a different case where it's another way to get constraints, but I do not expect you to use this for the current homework. So if constraints are unavoidable, this is the case where the number of generalized coordinates is greater than the number of degrees of freedom. So for example, this will come up if you have non-holonomic constraints. So if you have non-holonomic constraints, or if you if for whatever reason you didn't choose a minimal set of generalized coordinates. Remember, we said that if all your constraints are holonomic, you can always theoretically find a minimal set, but maybe it's hard to find, especially if you have a large dimensional system, in which case you just have to work out what these constraints are. So if you just, or I've put another one, if you just want to know the constraint forces. So if you have cases like this, like a non-holonomic constraint is how this is my little half cylinder, and then here's the full cylinder, a wheel. If I want to work out this dynamics in detail, how this thing rolls and kind of turns and stuff, I'm going to have more generalized coordinates than degrees of freedom. In this case, you write all the constraints whether holonomic or non-holonomic. That means whether they depended on just the generalized coordinates or if they also depended on generalized velocities. You write all the constraints in the non-holonomic form. You write all the constraints It's also technically called Pfaffian, which starts with a P, after a mechanician or mathematician named Pfaff. The Pfaffian form. The Pfaffian form is fun to say. All right, and what was this? The form of this, we'll have an index L that goes from 1 to the number of constraints, and we're writing all the constraints in non-holonomic form. So I'm using, there's capital S of them. And each constraint is of this form where you've got some function, these functions A that are functions of the Q's times Qi dot. So this is a term that's linear in the generalized velocities. We also allow the possibility that there's another term, which I'll write as A L T. This over thing is ALI. This is ALT. Could be a function of Q. So we're writing things in that form called Pfaffian form, or I just call it the non-holonomic form. So yeah, this ALI is it's a coefficient of the generalized velocity. And then even though there's a T here, you know, this thing might not be a function of T. This is just the traditional way it's written. So this is any term that's not a coefficient of a generalized velocity. Generalized velocity, Qi dot. And then what is S? S is the total number of constraints. This is different than the way we wrote things before, where we wrote the holonomic as K and the non-holonomic as S. We're now writing all the constraints in this non-holonomic form. And how would we do that? If we have a holonomic constraint, in how do we write it in non-holonomic form? So if we have a non-holonomic, a holonomic constraint, that'll be something that's a function of q and possibly time that equals 0. We then take the time derivative, the total derivative of this. So if phi equals 0, then the total derivative of phi also equals 0. And if you work out what this left-hand side gives you, it's going to look like something where there's some coefficients times qi dot plus some other coefficient. And so it's in the appropriate form, just by the chain rule. All right. So if we have a situation like this, I'll tell you the punchline. The punchline is on the right-hand side of Lagrange's equations, we add a generalized force of constraint. And we'll use capital C for this, C sub I. And it will look like this, a sum over the number of constraints. So L goes from 1 to S. We introduce these things called lambda L times A L I. These lambda L's are going to be new things we solve for called Lagrange multipliers. So these are new variables that we solve for. So to go back to Lagrange's equations now in all of its glory, if you do have constraints, so this is for the a system where we've written a Lagrangian. So we have total derivative of partial L partial qi dot minus partial L partial qi. Traditionally, that's on the left-hand side of Lagrange's equations, and that contains all inertial forces, so forces that are related to accelerations, and also any force that's from a potential energy. On the right-hand side, what did we have? We have the generalized forces that come from non-conservative Newtonian forces. And now we add these constraint forces, Ci, or we could just write it all out. I'll just write it again. Sum, L goes from 1 to the number of constraints, lambda L, A, L, I. So notice this index I is in each of the terms. I. Okay, and so I, this is the index of the generalized coordinate. So this goes from 1 to n. That means you have n of these equations. So these are Lagrange's equations when you've got more degrees of, more generalized coordinates than degrees of freedom, or in other words, you have constraints on your generalized coordinates. And the constraints are written in this form up here. So that's all fine and good. Let's try it on an example, right? Because this is abstract. I'm going to go back to an example I showed before. I think I showed it. I really like the baton, but this baton isn't the one that's sliding off the wall. This is the baton that's with the wheel under one of the masses. Let's see. None of this seems right. Okay. There we go. Yeah. So this is the baton or dumbbell with a wheel oriented the way that this line over here is oriented. So it's along the axis of the baton. So with a wheel under one of the masses. This puts a constraint on how that mass number one, can move. It's sometimes called a knife edge constraint because it's as if you have a knife edge or a skate, like ice skates, underneath that mass that forces that mass to only move in the direction that the blade is, not perpendicular to it. So it's sometimes called a knife edge constraint. We've got Q1, Q2, Q3. We've got 3 generalized coordinates, and they are, at least as we've chosen it here, X and Y for mass 1, and then that angle theta. So N equals 3. But there is S equals 1 constraint. And so the number of degrees of freedom is N minus S. So there's just 2 degrees of freedom here. That knife edge constraint, we've written it, I think we've written it before. It ends up looking like this. And there's an implied 0 times theta dot. So this constraint is in the form of that non-holonomic constraint up above. And we might, since there's only one constraint, we'll label this as L1. So that means this is writing it in the form of above A1, 1, because, right, X dot is actually Q1 dot. This is A1, 2, and this is Q2 dot. And this is A1, 3, which is 0, times Q3 dot. So it's in that form. That general form up above of A1I times Qi dot plus A1T equals 0. And there doesn't seem to be an A1T, so that's 0. And we know A11 is negative sine theta, A12 is cosine theta, A13 is 0. Okay. If we were to simulate or write the equations of motion for this system, this is all happening in the plane. So potential energy is 0. There's no applied forces, in fact. All there is kinetic energy. So the Lagrangian is the kinetic energy minus the potential energy. Potential energy 0, so this is just kinetic energy. What is the kinetic energy here? And this could be tricky. You write down the unconstrained kinetic energy. I think that is, whoa, I did not want to write it that way. Yeah, there we go. So you write the unconstrained kinetic energy. What does that mean? Don't apply this constraint formula. So you write this as 1/2. Let's say these have equal mass. So this is mass m. This is mass m. 1/2 m, the unconstrained velocity, particle 1, plus 1/2 m, the unconstrained velocity of particle 2. That's it. There's no rigid body stuff. And so this is going to be a kinetic energy that depends on the q's. and the q dots. And for the q's, I just write q. So since we're writing the unconstrained kinetic energy, that means write the unconstrained velocity. If you were to write those out, like what's the unconstrained velocity for 1? If you were to write that out, it would just be x dot squared plus y dot squared. Nothing related to theta. For the particle 2, you do some trig and stuff and you'll find out what that is. L squared theta dot squared minus 2L x dot theta dot plus 2L y dot theta dot cosine theta. I think I'm missing a sign. I'll just move this guy over. Sine theta. All right. You plug that in. So we would have a Lagrangian that's let's see. Am I missing something here? I may be missing something here. I think this will be also x dot plus y dot squared plus. Sorry about that. And then we would have, you add everything up, you have m x dot squared plus y dot squared plus 1/2 m L squared theta dot squared minus 2L x dot theta dot. As long as I'm turning the crank appropriately, there's nothing here to memorize. So that's my Lagrangian. I would have I have 3 Lagrange's equations of motion, right? Because I've got I goes from 1 to 3. So what's that going to be? Take the total derivative, partial L, partial QI dot, minus partial L, partial QI equals, and now, what do I have on the right-hand side? There's no non-conservative force. There is a constraint force. Let me sneak up here to remember what that constraint force is going to look like. Sum from L goes from 1 to S. Well, I only have 1. S is 1. So that'll be lambda 1 times A1I. Okay. Lambda 1 A1I. I is 1, 2, 3. And so now what do I have? I have, this is 3 equations, right? But then this is also an equation up here. So the boxed equations, I have 3 of them. And I have, 4 of them. And I have 4 unknowns. So the 3 Lagrange's equations plus the 1 constraint equation equals 4 equations. So do I have a closed system? And I have 4 unknowns. They are, this is how you think about it, the x double dot, y double dot, theta double dot, and then lambda 1. So I've got 4 equations, 4 unknowns. I can solve for them and figure it all out. And get the dynamics. If I simulated this, whoa. I don't know what happened there. See if it erased everything. No. Okay, it's good. So I can simulate this in MATLAB for some initial conditions. And where is it? Here it is. Oh my God. Yeah, that's some code for it. So I gave this an initial condition where it's, so mass 1 is at the origin. That's the one with the blade under it. Mass 2 is the one that can freely slide. That's at 1, 0. I'm giving this a shove backwards with a little bit of a spin. So theta dot is initially non-zero, and so the velocity is going backwards. And so you can see what this does. We're sort of tracing what x and y does. That's the middle of the mass with the blade. So if you remember when we talked about the shopping cart instability, this thing displays the shopping cart instability. When you shove it backwards, and in this case, give it a little bit of a spin too, it always orients itself so that the blade is in the back. And it's always very characteristic of these types of systems that there's a cusp. You see this cusp, that cusp near the beginning is related to this thing reorienting. And non-holonomic systems often have this. Okay. Oops. So let's just count the equations in the unknowns. For these types of systems, we've got n Lagrange's equations plus s constraint equations. It's a number of equations. What about the unknowns? We've got n q I double dots plus we've got s Lagrange multipliers. So we've got n plus s equations and n plus s unknowns. So you can solve for these systems and work it out. Let's see. What do we want to say about this? There is some, yeah, we could try to interpret, do some interpretation of what's going on. Yeah. So let's just do some. This might be helpful. Interpretation of the non-holonomic constraints. And if you're looking for a place to read, so Greenwood, there's a certain part there. All right, I'll show my this baton with the blade under it because it's simple enough. here's what we can do. Let me just write this in the normal color. We can imagine constraint surfaces in velocity space. So we've talked about phase space. Now you need to think of velocity space. Okay. We can imagine constraint surfaces in generalized velocity space. But yeah, let's just say velocity space. So for this system, I think we've mentioned it before. We write, if you were to write the unconstrained velocity, that would be V1. And V1 is x dot, y dot, written in an inertial frame. And we're saying there can't be any motion in this normal direction to the blade. So n hat is at least, yeah, if we were to write what n hat is, it's a unit vector. And it could be written in terms of the coordinate theta. So V1 dotted with n hat, we could write this as x dot y dot transpose times negative sine theta cosine theta, and that equals, right, this thing that we wrote up above. And it equals 0. What does this mean? Let me write velocity space. In velocity space, what I mean by that is, let's write x dot and y dot. We can't move in just any direction. Here is n hat, and we can only move in a locally on a constraint surface. In this case, it's a constraint curve. This orange curve, it's the instantaneous constraint plane. It tells us instantaneously what direction our velocities can be. It could only be in this direction. Now, as theta changes due to dynamics, that instantaneous constraint plane will change. But we can't just move in any old direction. So we could also view this in configuration space. That means the generalized coordinate space. The space of the cues. So let me get some figures. Unfortunately, this isn't in the book. It's in some other book that has a different purpose. But this sort of gives the idea. So maybe look first at this B over here. If my angle, if I just keep changing my angle, the little plane here indicates the direction that I can kind of instantaneously move. So over here, this is at theta equals 0. If theta equals 0, then I can only move locally in the x direction. If over here, if theta equals pi over 2, well, I can only move locally in the y direction. And if I'm somewhere in between, like in this case, then I'm moving in some direction that's between pure x and pure y. And this is true. So think of the theta equals 0 plane. The theta equals 0 plane is just populated by a bunch of these local directions, and that's what's being shown over here. So this is the bottom rung, the bottom plane. This is theta equals 0. For theta equals 0, no matter where I am in configuration space, I can only move locally in the x direction. And the theta equals pi over 2 plane, well, I can only move locally in the y direction. And anything in between will be some other combination. Which then brings up the question, can I go from any, let's say I have my baton in some initial orientation at a certain x and y. Can I get to any other orientation? I don't know. This is a question. This is maybe nobody knows. You have to do some kind of weird path, oops, to go from one spot to another in when you've got these constraints. So if I'm at, this is the way to think about it. If I am starting here at the point A, and all I want to do is move side, I'm at A, and A is at, also has an angle theta equals 0. If I want to get to the point E, which would mean a sideways move, so think of it as, here's X and Y. My point A, this is point A, and I just want to move sideways. In some sense, I want to like parallel park. I want to parallel park. I just want to go from here to here. Is that possible? Well, I can't just slide sideways. I have to do some kind of weird shimmying motion where I go forward, and I've rotated some, and then somehow back up. Just like you would for a parallel parking situation. Like I probably drew it wrong. Most of you maybe have parallel parked, right? You go up and then maybe you twist and then, okay. So this is completely analogous to parallel parking. And if you haven't noticed, cars do not have wheels that go sideways. So you have to do something funny to parallel park. So it's analogous to, let's call it the problem of parallel parking. And if you're like me, this is a problem. I don't like parallel parking. It's, you know, I don't like going to crowded cities, just so I could avoid parallel parking. Here is a parallel parking animation. If you've forgotten what it is, you're like, I want to park there. So you have to do this weird thing. And then here's how you leave. Is there a way to freeze this? No, I can't freeze it. But it's you might not realize what you're doing, but you're doing something related to non-holonomic constraints. So if this is the curb, and here's like the car, here's another car, and you're like, I could fit right there between the two. If I'm right here, unfortunately, because of the constraints of how my wheels go, I can't just do a sideways displacement. I have to do this weird thing where I go forward, and then stop, and then I go backward, and with this bit of a turn, and then maybe I have to adjust a little bit so that I can get my car here. So yes, I can go sideways, but I have to do this sort of strange motion in velocity space to achieve it, which you're not thinking about that when you parallel park. You're like, I'm just doing what I learned. But you have to do some weird loop in configuration space. Like, look at this picture on the right. You have to go through this crazy loop just to get a small displacement in one of the variables. So, oh well, that's life. An interesting thing about parallel parking, and this has to do with the limits of modeling. When we do modeling, you've probably seen this a lot, we linearize about our current state. Well, a linear analysis would never tell you about parallel parking. because you'd say, oh, instantaneously, if I'm here, linearizing, all I can do is go forward or turn a little bit. There's no way I could go sideways. So parallel parking is an inherently nonlinear phenomenon that if all we wore were, linearized glasses of the world, we'd never know how to do it. So there's interesting questions related to accessibility of configuration space when you have constraints. And this is often it's a problem in control. I think there are situations where not all, depending on your initial condition, only certain parts of configuration space are available. For the case of the car or the baton, I think every location and orientation is possible to reach from any other initial condition as long as you do it right. But like when you have the car, you've got the steering, and even though we've got two wheels up front, you could just view those as it's one wheel, and then the back wheels, let's say, don't move. So you've got your two controls. If you've been in a car, you know that you've got steering and the acceleration, the pedal. But to get the car in any old configuration, there's three variables. You've got X and Y. Think of that as X and Y of the center of the car, and the car's orientation. So you have three configuration variables. And there's fancy stuff that controls people do to figure out if you've got fewer controls than configuration variables, is every X, Y, and theta accessible? For a car, we all know the possibilities, but let's say you're talking about a satellite or some aerial vehicle or underwater vehicle or something else. You have to use some other math. So that's just something to keep in mind. We'll talk more about forces of constraint and interpreting them in terms of the usual Newtonian forces and Newtonian moments next time.